Okay, now Feynman propagator, that is what we would like try to derive. We want to deal with these kind of objects, multiplication of 2 operators or in fact 4 operators. So, we want to construct Green's function. No, Green's function involves such things, or a correlation function will involve like this: phi x, phi y, or I have phi x, phi y, phi z, like that, you know. So, that kind of, so we need these kind of operators in future, is bit shifted. So, we always want the left operator, this operator, to be at a later time. This x naught is a time coordinate in relativity. So, x naught, x1, x2, x3. So, these are position and this is time. So, x naught and y naught represent time. So, here this, when I put a t, this is called time ordered. So, the time ordered product. So, when I put this t, I can flip it around. I can, so you see here I have phi x, phi y and phi y, phi x both. So, this one involves, the top one is when x0 is greater than y0 and the bottom one is when y0 is greater than x0. So, you, well, basically what do I do when you operate? First state acts on this, then acts on that, no, acts here first, then second. I want the second time to be later than first. So, that is called time ordered. Okay, so that is what written here. Now, it can also be written, so this is basically the Green's function. So, you write for a given, well, basically I want a number. So, this is the operator, but the Green's function is a function, is a number, right. So, I will be acting on some state, or it could be a vacuum state. Okay, I hope I am not losing you. So, these two things become like that. So, theta is a step function. So, y0 minus x0, what does theta means? This one means here y0 is greater than x0, only then it is 1. This object is like that. So, this is y0 minus x0. So, when y0 is greater than x0, then we get 1, otherwise we get 0. So, so this is the first part and this is the second part. Here x0 is greater than y0 to be 1 and we get that. Okay. So, this is how we compute Green's function, and this is the time ordered propagator, time ordered product. Okay, do not be too afraid of this, but this is what it is. So, let us really compute. Okay, now this will probably make it more, you will get a better feel for it. In fact, this slide is a nice important slide. So, remember I had written these operators, no, for 5. So, these are operators, phi dagger operator and 5 operators. So, phi dagger operator remains, well, I did it probably too fast, a dagger p exponential I px py and b dagger p bp and exponential minus py. So, you can just look at your note, that is what it is. Now, this operator operates on vacuum. So, when it operates on vacuum, well, these are all C numbers, no, these are complex numbers. So, the operator will act on vacuum. So, a dagger p will act and bp will act. So, what does bp 0 will give you? It is a destruction operator on vacuum 0, right. So, this is 0. So, will act on this, and what will this give you? A dagger p 0 is will give you p, it will create a particle with wave number p. Okay. So, in vacuum we create a particle, that this is a creation operator, it is a particle, not antiparticle, it is a particle. So, that is what we have in the next line. So, this is it, this is a p and exponential IPY. So, this phase will also be there. Okay. Now, let us look at phi x, but it is acting on left. Okay. So, now this will act. So, I just write down phi x, which I am phi x I am just copying from my previous line, it is this. Okay. I am changing my dummy variable q to q, because I want to differentiate. This is a integration variable, so I just change it. So, 0 acting on this bra 0. Okay. So, what will happen now? AQ will work, give you non-zero. So, in fact, the idea is to just transpose it. So, this becomes A dagger Q get 0 and this is Q. So, now bring it back. So, this is basically, this will give non-zero and this will give 0, because if I transpose it, then I get BQ acting on 0, which will be 0. So, this basically is only for particles. See, my operator has both particle and antiparticle, but in this operation I am only working with particles by this construction. So, this is basically giving us Q, and please keep the phase, this is minus Qx. Okay. So, particle. So, I create a particle here and okay, here also, well, this is in the left part. Okay. Now, I am going to combine these two. So, this is a state and this is another state, brush state, ket state, and I just multiply. So, what is going to happen? The C numbers, and I am going to get P and Q, and two integrals dqp, dqq, and this is 2EP. Well, basically square root 2EP square root TQ exponential minus plus I P minus Q, Py minus IQX exponential IPy minus IQX. What is this? The delta function, no? So, delta P minus Q. So, P must be equal to Q. So, this is going to act on this, is going to be I. So, let us put x minus y. So, minus I Q x minus y. Okay. So, I just put P equal to Q and one integral is gone. So, I get this. Well, I put Q equal to P, so I can put like that. Okay. So, minus I P x minus y this. So, this is basically working with particles, and remember x is later than y. Okay. So, how do I write the diagrams? This is Feynman diagram. So, this particle is created here. Phi dagger is creating a particle, no, is particle P. Okay, this is the first operates, creates a particle, then it goes here and it gets destroyed. So, at x it is destroyed here. So, this particle has this lifetime in this region only. Okay. Please do not think what is this guy doing. So, if you want to think on those lines, the idea is there is an electron or there is a particle going like that, and it creates a virtual particle. It could be photon or it could be pion or something, and then another particle comes and it absorbs this particle. So, particle 1, particle 2 comes and absorbs this particle 2, this pion, and it goes there. Okay. So, this is for this virtual particle, for this particle, it is not connected with that. So, normally Feynman was doing for a photon. So, all these are for construction for photon, but I am not thinking of photon right now, I am thinking of a scalar particle with mass m. Okay. But this is a technology. Okay. So, the technology can apply in other places too. We are just thinking of tools, how to do it. All right. So, this is for particle. Well, this is one, but now here x is greater than y and I have phi x, phi dagger y. What if I flip it? Well, by the way, this is called advanced Green's function, is going forward in time. So, this particle is going forward in time. Okay. So, you see this time axis and time is going ahead, right, time is going like that. So, this time is later and this is before. This coil is forward in time, and I am going to show you a little later. Okay. So, in fact, the Green's function, we do all this labor, you will find something which we already got for PDE, but all this work is useful and important, because this is working with quantum field theory, we are discussing particles. So, we can't really say, well, what I did for PDE will work here. Well, it happens that we get the same function, but this technology is very important. So, now let us do it the other way around. So, I lack phi x y acting on 0. Okay. So, now this phi x operator is that this one. So, which will give non-zero value? Among the two, there is a q and a b dagger q. B dagger q, right, because a q 0 vacuum is going to be give 0. So, b dagger q, but b dagger is antiparticle. So, it creates a antiparticle with wave number q, clear, and it comes as plus iq, there is no minus sign here. Now, I apply phi dagger y acting on bra 0. So, which one will be non-zero? So, this one will be non-zero, right, EP. So, this antiparticle with wave number p is a destruction of antiparticle. Okay. Now, combine the two, phi dagger y, phi x 0. Okay. So, phi x is first, but it creates a antiparticle. So, this antiparticle is created here at x, this time axis. Okay. Now, then phi dagger y, whether it is a dagger, but it destroys antiparticle. So, dagger normally you think that it should be creating, no, but it is destroying antiparticle, destroying it. So, it destroys it here. So, it is created here and is destroyed there, and it goes that way. So, antiparticle goes forward in time, but if you want to think of particle, then the particle is going like that. Particle is going backward, and this is advanced time compared to this, no. So, this is the later time. So, from future it is going back. Of course, these are virtual particles, they are not really something is going, and these are only technology. So, these are all misnomer, the virtual particles are created, why is it going back in time, I create a time machine, none of it is possible. Okay. So, this is a tools to make computation. Virtual particle in some sense is also a tool, it is not there is a particle there, it is basically mathematical construction, Green's function, but final results are meaningful results, but these are technologies which we need to compute numbers. Okay. So, here I get this object. So, very similar thing that I get a IP x minus y. In earlier slide it was minus, and here it is plus. Okay. So, this is antiparticle which is going from x to y. So, this is first and this is later for antiparticle, but if you think of particle, then it is going back. Okay. So, that is the technology which Feynman created, but there are other two people we did simultaneously, Swinger and Tomanaga, but Swinger was doing all with Green's function, full integral and so on, and it did not catch on as much. Swinger is also considered very smart man, okay, very highly respected physicist, but these diagrams are Feynman's diagrams. So, that caught on, he became more popular. Okay. So, this is called G minus for if you think of particle, then it is a going back in time, and it is called retarded potential, retarded Green's function, and well, these are some names, but you should get the idea what it is. Okay. Now, I can do bit more algebra. This is a bit tiring, I mean I am skipping a lot of details, but all of it is there in that QFT for gifted amateurs. So, this is the time order product. So, remember it has two parts. So, you need to keep both particle and antiparticle, you need to do that algebra, no. So, this is why these are two terms. If you keep only one term, then you can't get the whole physics. Okay, so that is what you should think intuitively. So, these are the two terms which we derived right now. Okay. Now, we can also write down theta function like that using complex variables. No? Okay. If you substitute it there, then and do algebra, which I will skip, we get like that. Okay. So, this is coming from theta function. If you just plug this theta function appropriately and do the algebra and do this contour integrals and so on, you get this. Now, this is energy, no, P naught is energy, and P1, P2, P3 are 3 momentums. So, you get energy minus EP squared. Okay. E for energy for particle with momentum P. Now, E squared. Okay. So, E square, EP squared is P squared plus M squared. This is Einstein formula, no, energy is okay. So, what is E squared minus P squared? This P, well, this P vector square, no, P vector square minus M squared. What is E squared minus P squared? Is a called, okay. So, this is called P mu square or 4 momentum square. You guys are familiar with this? Okay. So, we have time and space vector. So, you can consider T squared and X squared. These two quantities are not invariant under Lorentz transformation, right. So, if you have one coordinate system which measures T and X, you can compute T squared and compute X squared, well, delta T squared, 2 events, delta T squared, delta X squared. These are not constant. For Galilean transformation or classical physics, delta T is constant, right. 2 events, the time difference must be constant, but relativity is not. But what is invariant is delta T squared minus delta X squared with appropriate C square multiplication. This is constant. Similarly, for relativity, E and P transform under Lorentz transformation. You will get different E, different P. If I do go to Lorentz transformation, that means you give a boost, but the P mu squared, which is E squared minus P squared, is constant. The Lorentz invariant, and they are very important for various reasons and also theoretically. So, this is what we write P squared, this is the P mu squared, this is not 3 momentum squared, this is E squared minus P squared minus M squared. Okay. So, this quantity is so this is what we get. Now, you may recall what is this. Let us go back to our equation. Our equation is dt squared minus Laplacian square plus M squared, right. Psi is 0. Now, so this is basically the Green's function, G inverse, Green's function inverse. So, this guy will give us dt squared will give us minus omega squared I omega. Laplacian will give us k squared plus M squared. Okay. So, if I go to relativity, then this becomes, so this is only the sign stuff, minus E squared plus P squared plus M squared. Okay. Now, I change the sign. Okay. Sign changes with me, I can put Green's function definition as well. So, this is E squared minus P squared minus M squared with a minus sign. Okay. So, this is what I got here, E squared minus P squared, which is here. So, this guy is basically, not basically, it is exactly this. Okay. So, this is the Green's function and we derived it with the partial differential equation. Okay. So, with all this machinery, we basically get the same Green's function. Okay. So, This is called Feynman propagator. This is, you should know this word, this Feynman propagator. Okay. Of course, this for quantum field theory, but it's interesting that this we get the same thing with a differential equation. Okay. Now, let me just get for, okay. Now, this combination of two diagrams, this one forward Green's function, and this is a advanced Green's function, retarded Green's function, together it gives you that. Okay. So, this combination deals with particle, antiparticle, together. Okay. So, this is our propagator or Green's function. Now, Green's functions are like represent interactions. Okay. Now, this interaction was very important, and this called Yukawa. Okay. If I do the Fourier transform of this, what will I get? Go to real space. This is momentum k omega space. I can do the inverse, invert it. Okay. So, you have to go to, well, basically suppressed omega, and you write this is only p squared minus m squared. Keep omega 0. Okay. So, what is 1 over p squared? Green's function, this is Green's function in or k squared. You remember this? No, I think this is Green's, well, g of k 1 over k squared. What is the g of r? Is 1 over r. It's a Coulomb interaction. Okay, 1 over r. Okay, you can if in 3D. So, the way to see this is well, one simple way I told you to do dimension analysis, e to power I k dot r d cube k, right, that is what it is. So, this is going to give us by dimensionally k on top, it is a dimension of k on top. So, k has dimension of 1 by length. So, this is 1 by r. Okay. This is Coulomb, I mean particle electromagnetic field, this is the Coulomb interaction, Green's function. Now, what I put, well, there is a plus here actually, omega squared minus k squared minus m squared. Okay. So, k squared plus m squared. So, this one I mentioned in my lectures is going to be 1 over k squared plus m squared leads to exponential minus mr by r. Okay. And remember, we have this p squared is coming as e squared minus, so the omega squared minus k squared, no, minus m squared. So, e squared minus p squared minus m squared, set omega to 0, omega is small. So, you get k squared plus m squared, which is this. So, this shielding of the Coulomb potential. Okay. So, this what is a Green's function in real space, or is interaction in real space. So, what we drew this diagram like that, like that, like this. So, these are supposed to be nuclei. This could be proton and neutrons. In fact, this was the idea by Yukawa. He won the Nobel Prize for this. So, protons and 2 protons and 2 neutrons in helium nuclei, they are not repelling each other. Well, there is a repulsion, Coulomb repulsion, but Coulomb repulsion is so strong that it could basically break the nucleus, right. So, what is holding them together? Okay, there must be some other force which is holding them together, and Yukawa postulated that there is another force which is short range, and that force is going like that. This whose Green's function is this. Okay, and from here you can compute the mass, right? You know the r, then you know the mass. R you can set as the size of the nucleus. Okay, so you can, well, I mean this is Yukawa's work. So, you can get mass, and he postulated some mass, and they in fact they indeed found a particle with that mass, and these are pions, I think so, some these mesons particles, and that is the interaction. This is the particle which corresponds to this Green's function. Okay. So, this algebra or this field theory is not useless, they are very important, and this is what is the potential for this. No, I am sorry, not R by M, this is MR, M should be on top. Okay. And so, Yukawa, this is called Yukawa potential, is not only for it is also in atoms. We have screening of electrons do not see the Coulomb interaction, but they see lowered interaction because the electrons are being shielded by other electrons. So, this is very important interaction. Okay. So, I think we will end with one homework I am going to give you. By the way, this homework please do it. So, and please revise your Green's function, midsem is coming close. So, all this was relativistic. Okay. So, this is full relativity, which I did not in more detail, which will require more lectures, but can we derive non-relativistic limits or Schrodinger equation from these formalism? It turns out it can be done. So, this relativistic wave function, we replace this by psi non-relativistic multiplied by exponential minus IET by h bar. Okay. And this energy, we say that, well, kinetic energy is too small, means half m squared is too small compared to mc squared. So, we just put mc squared here. Now, we can substitute this in the Lagrangian for the Klein-Gordon. We have written the Klein-Gordon Lagrangian, or you can put this in the Klein-Gordon equation, okay, and then you should derive Schrodinger equation, right. So, if you substitute it, the mc square term will go away, and you should be able to, under appropriate approximation, you should derive Schrodinger equation for psi n r, derive the Lagrangian. Okay. So, you should be able to do it. Okay. So, we will end here, and I can take some questions. Keep the recording on for, let us see how is the questions coming, how are the questions coming. So, questions? It is all clear, is it, or is it nothing is clear? Huh? Okay, no, it is a difficult thing, but so read up that book. That book is, but well, it's difficult. It's not. I mean, I tried to. So maybe you can turn off the recording.